Now we're going to present a second proof to the theorem that if f is continuous on a closed finite interval, then f is bounded on that interval. The reason we present a second proof is just that this theorem happens to have two very interesting proofs, and there's no reason to miss out on either one of them. Now, the second theorem will use part of the first theorem. We specifically will use the two principles we stated. It also uses something else, however, that it will use the nest theorem that was mentioned in a previous chapter that says if you have a bunch of nested intervals, which is if you have a bunch of closed intervals, each one is completely including the next one, so it gets smaller and smaller. And not just that, the length of the intervals has to go to 0. Then there exists exactly one point that belongs to all these intervals, that they have one point in common. Okay, the proof will proceed as a proof by contradiction. Now let's look at the number. Okay, we have a line. And then on line there's a and b, which is a closed interval. What we're going to do is assume that f is not bounded. Let's say f is not bounded and see what happens. Assume f is not bounded. So if you assume that f is not bounded, then on the interval a to b, what we're going to do is cut the interval in half at some midpoint. And we will define the intervals like this. We will define this nested interval, and we will define I0 to be the original interval from a to b. Now I1 we'll define it to be either half. Okay, we'll cut I0 in half. I1 will be the half of the interval, either half, where f is not bounded. Because since f is not bounded on the whole interval, it has to be not bounded on at least one of them. If it's bounded on both of them, then by principle number 2 of the last proof, it has to be bounded on the whole. So it has to be at least one half where it's not bounded, and we will name I1 to be either half, that where f is not bounded. If it's not bounded on both of them, then we can just pick whichever one. Doesn't actually matter. The point is I1 that's chosen is inside I0, as this condition requires. And then we'll continue doing this. Then we cut I1 in half, okay? And then create I2 the same way. I2 will be the half of I1, where f is not bounded. And so on. And continuing, we will continuing to choose this thing such that, so we have this nest starting at I0, which contains I1 and I2, and so on and so forth. It keeps going forever. In each time we cut the interval into half, where f is not bounded on any of these things. Now by the theorem, first we have to show that in is equal to 0, but the length of in is is clearly going to 0. Since you're cutting things in half, they don't exist very long. So the length of in, and you can even calculate it if you want, is just equal to the length of the original over 2 to the power n. So that's clearly going to 0. So that condition is being satisfied. And then this formula is not that interesting. It's pretty obvious it's going to 0. So then we have this entire theorem's condition satisfied. So there exists, by the theorem, there exists exactly one point. Point, we'll name it C, that belongs to all in. Okay, for all n. All right. Now we will appeal to principle number 1 in the last proof, which says any point that's inside this interval has a tiny little neighborhood, an interval that where f is bounded, or we call it this way. By principle number 1, we'll write down, that's from the previous proof. By principle number 1, then we have, there exists a certain interval J, instead of using delta, we'll just say roughly there's an interval. Okay, it's actually the delta interval. J where C is in J and F is bounded on J. All right. If that is the case, well, what is the problem with that? The problem is that C is on, because the IN is going down to 0, there exists, okay, because C belongs to IN, okay, since C is an element of each IN, and IN is going, length of IN is going to 0, the length, say absolute value, is going to 0, that means there exists IN, there exists a large enough N where IN is completely included inside J. Okay, this interval is completely inside because each N is getting so much smaller and J is not getting any smaller. So eventually you'll be able to fit it in completely. Now that would mean, however, that F is not bounded. But F is not bounded on IN or J. Because if it's not bounded on IN, this big N, then it's not bounded on J. Which of course is a contradiction because we already said F is bounded on J. Now we come up with F is not bounded on J, so you got a problem, which proves our theorem, that is, if F is continuous on a closed interval, then it must be bounded on that interval.